All right, let's talk about valence electrons. And I want to introduce the octet rule for those of you who haven't seen it before. So we said that valence electrons are the highest energy electrons on an atom. So that's these valence electrons. So these are in the outermost shell, highest energy. And we as chemists care about valence electrons because they're involved in all the chemical bonding, they're involved in chemical reactions. They're just incredibly important for understanding chemical processes. And so these highest energy electrons can be correlated to the position of the element that they're on the periodic table. And we talked a little bit about this if you've seen the series of videos on orbital diagrams and electron configurations. When we're thinking about the electron configurations for the main group elements, so the main group elements are your group A's. There's a couple different ways that we can number the groups or the families on the periodic table. We can go 1 through 18, so from the alkali metals to the noble gases. Or we can have 1A and 2A, which are over here. The group B metals are your transition metals. And then groups 3A through 8A here. Now, the A's and the B's are kind of a nice way to delineate the different groups on the periodic table because they give you information about the number of valence electrons that are there. If we think about the electron configuration for everything that's in the alkali metal column, then the alkali metals include things like sodium and potassium and rubidium and all those good ones. And all of their electron configurations end with kind of whatever the period number they're in, S1. So that'd be, N, whatever the period number is, S1, meaning there's one electron in their highest energy s orbital. Everything in the alkaline earth metals ends with N, again, whatever period number it's in, S2. Now if we go and hop across, because this is our D block if we're thinking in terms of electron configurations, so we have our D block here. So we're going to ignore this for the time being, and we're going to focus on the group A kind of elements, the main group or representative elements. Then we hop across, and whatever D's are present, but they're not really involved in bonding. So for these guys, we have S2, we have a full S because we had to get through the S block in order to get to them. And then now we're in the P block, and we're in the first column in the P block, so there's one electron. And again, this would be at whatever N value here. So if this was in the fourth period, this would be 4s2, 4p1, for example. If we hop over here, we still have a full S, and we have 2 in our second column here for the P block. And then we have full S3, full S4, full S5, again, just kind of counting over, and whatever period we're in is going to give you the N value that's in front of each of these. I'm just kind of focusing on the electrons in the orbitals here. And then when we get to the noble gases in column 18 or 8A, then we have a full S and a full P, which would be 6 in the P orbitals. All right, now if we look at the relationship between the number of electrons that there are, right, based on now we know how to use the periodic table to find these electron configurations. These electron configurations tell us where on the atom these electrons are. And now we know the highest energy electrons for each of these columns are always going to be the same, just kind of their location with respect to the nucleus is what changes. Then now I can see that I have 1 valence electron in the first column, 2 in the second, 3 in 3A, 4 in 4A, 5 in 5A, etc., right? So kind of a cool pattern. Again, how powerful is the periodic table? So if you know these valence electrons, then this is going to give you some interesting information about what the elements want to do and what they want to be and how they want to react with other things. And one of the guiding principles we use to talk about kind of what these valence electrons can tell us about the chemical reactions and the chemical processes and the chemical relationships that there are is called the Octet Rule. I like to think about this as really an octet guideline in sort of the Pirates of the Caribbean sense, that it's kind of a guideline, less of like a solid rule or law. The Octet Rule says that elements want to beg, borrow, and steal in order to look like a noble gas. And what they want to beg, borrow, or steal is electrons. And when I say that they want to look like a noble gas, what I mean is that they want to have a full valence. So if everyone wants to look like the elements that are in column 18 or 8A, then they want to try to get to 8 electrons in their valence. That's the general rule. Of course, there's some exceptions to that, and we'll kind of talk about those throughout the course of our discussions on chemistry. But that's where the octet part comes, right? So in general, this means that they want 8 valence electrons. They want to look like a noble gas. Everyone wants to be a noble. We want to look like a noble gas. So they're either going to, and I say beg, borrow, steal, what I really mean is that they're either going to pull electrons away from something else, so they're going to beg for them. They're going to borrow electrons from someone else. Maybe they're going to share them. Or they're going to steal electrons from someone else, and maybe they're going to grab them, right? So we kind of have this combination of I'll either give them up, I will share them, or I will take them, right? Okay, so if we are messing with the number of electrons, then if everyone is trying to get to 8, then it's all going to be a balancing act of, is it easier to get more electrons and look like the noble gas, or is it easier to lose electrons and look like the noble gas that comes prior to? So there's this kind of counterbalance to everything. So if I start in column 1 here, in group 1, our alkali metals, if my highest energy electron is just 1, it's probably going to be easier to just lose that 1 and get to the noble gas that comes before it than to gain 7 and try to get to this guy. Well, and actually, depending on where you are on the periodic table, it's more than 7 because you'd have to get all these d electrons as well, right? So hopefully that's kind of obvious that it's easier to lose the 1, or at least intuitive if not obvious, lose the 1 than to gain 7. If I lose 1 electron, so let's take sodium for an example. Sodium has 11 protons, and a neutral atom of sodium has 11 electrons. And the electron configuration for that is 1s2, 2s2, 2p6, that accounts for 10, 3s1, right? That 3s1 tells me where it is on the periodic table. It's in the 3rd period. It's in the 1st column in the s block. Now, if I lose this highest energy electron, that's my valence electron, then now I will have 11 protons still. It's still sodium. That's a unique identifying feature of sodium. But now I have 10 electrons. If I think about the net charge here, then this is going to give me a net positive charge because I have more plus signs than minus signs if we think about them this way. And if I think about my electron configuration, now I've lost that 1 electron, right? I have a net positive charge. And now this is my new electron configuration. That net positive charge is going to give me a positive charge that looks like this, where the sign is the superscript. That tells me this sodium has a +1 or 1 fewer electrons than it does protons. And that's going to be true of anything in that first column. Easier to lose that 1. And when you lose a negative charge, you become positively charged. Now, just as a side note before we kind of delve into the implications across the periodic table, if I was to just give you this electron configuration, you would look at it and say 2, 4, 10 electrons. If I was to look at the periodic table, and I'd say, well, how many, what element would that be? You might say, well, it's neon, right? That has 10 electrons when it's neutral. This is the electron configuration for neon, but it's also the electron configuration for sodium plus, right? So that's sodium, what is called ion, and ions are charged atoms. So atoms or elements that have fewer or more electrons than they normally do would have a charge on them, and we call those ions. We say that neon and this sodium ion are isoelectronic. Isoelectronic, it's a great vocab word. Isoelectronic. That prefix iso means the same. Electrons means that we have the same electron configuration. So we'd say that neon and sodium are isoelectronic to each other. All right, now let's go back to the implications here on our periodic table. If we think about sodium, we said it was easier to lose that one electron. And so if we bring my column headings there, then everything in this column is going to want to form a +1 charge when it forms an ion. So let's kind of make a row here. Now let's go to the second one. Do you think it's going to be easier to gain 6 electrons or to lose 2? Well, cost-benefit analysis probably says that it's easier to lose 2 electrons. If I lose 2 negative charges, I become positively 2 charged. Now again, let's kind of ignore our transition metals. They have their own issues with those shifty d electrons, which kind of do their own thing and cause all sorts of weirdness. Let's hop over to our column 13. We have 3. It's easier to lose 3 than it is to gain 5. So when I lose 3 electrons, that gives me a net +3 charge. Now you get to 14, and again, the octet rule says we want to kind of beg, borrow, and steal in order to get to 8 valence electrons, because everyone wants to be a noble gas. And if I have 4 already, then it's probably just as easy or likely to gain 4 or lose 4. If I lose 4, then I have a net positive charge, right? I lose negative charges and I get positively charged. If I gain 4, then I get a net negative charge. So this column can kind of go both ways. There's a few different metalloids in there. The metalloids tend to be exceptions to rules as well. All right, we have 5 electrons here. Now we've kind of flipped it. Once I have 5, now it's easier to gain 3 than it is to lose all 5. If I gain 3 negative charges, that gives me a net -3 charge. And then kind of same logic applies. I have 6, easier to gain 2, 7, easier to gain 1. And the noble gases, and we've talked about this before, are inert. They don't like to interact with anything else. They are noble. They can't be bothered with the rest of the riffraff on the periodic table. And part of the reason for that is because of the octet rule, right? Everyone wants to be a noble gas. The noble gases are already noble gases. So they don't have to do anything electronically with electrons in order to do that. So they're already happy as is. They don't like to form ions for that reason. So we tend to kind of ignore the noble gases when it comes to anything dealing with charged atoms, charged particles. So these charged atoms, we said, are called ions. There's 2 different types. We have cations, which are positively charged. Which means that we've lost electrons in order to get to them. Right? We lost a negative charge in order to get positively charged. And we have anions, which are negatively charged, which means that they've gained electrons. So we're getting more negative particles. That means that we are negatively charged. Cations, anions. The way that I remember these is because I'm kind of a crazy cat lady, and so I'm very positive about cats. You may not be very positive about cats, but cats themselves have pos, right? They're positively charged, so that may help in terms of your memory there. Once you've gotten the terms cations and anions down, it makes it hard to see other terms that have similar endings. I, as a chemist, tend to struggle with the word anion or union, right? And then in recipes, I get a little confused sometimes when I see anions, but so that always takes me a second as well. So not actual chemical terms. All right, so cations are positively charged, anions are negatively charged. They're going to gain and lose electrons in accordance with this pattern in order to try to fulfill the octet rule. That's kind of the name of the game for using our electron configurations to predict ionic charge.